All right. Good. We got voice here. All right. So 1982, it says a buffer solution contains 0.4 mole of formic acid and 0.6 mole of sodium formate in 1 liter of solution. The ionization constant, the Ka for the formic acid, is 1.8 times 10 to the negative 4. So it's not that negative 5, but negative 4 this time. So they love playing with that number. All right, so A says calculate the pH of this solution. So we've got a strong salt, it looks like. So let's start with that. So we need to take our sodium formate and break it apart into sodium and.
So this might seem like kind of a weird question.
I don't know why they put it on the end. Is that what you're asking?
Yeah.
Why is this? I don't know. That I've always wondered that, but hey, the 80s were crazy, so I don't know.
That's fair.
I don't even want to try to imagine what they're doing there, or if they're trying to preserve the H. But I mean, there's 2 H's on here, so we don't need to like worry about. I don't know. Don't worry about it. I haven't seen it in the 2000s, thank God. All right, so we.
Use that molecule among others to spell cocoon metal.
Okay, and so we've got our formic acid, the HCOOH. That breaks apart into hydrogen and that. And we have 0.4 moles of the formic acid in 1 liter. Boy, that's nice. That's easy to do. Come on, what are you doing? Scoot over. There we go. So we've got 0.4 of that. We don't know what we have there. We're going to find that. And 0.6 of that. Actually, let's just say that's at the end point. So we're going to solve for that. So, that's an ugly bracket. So let's get our Ka, which is hydrogen, formate.
We also use the
Anderson-Hasselbalch?
Yes.
Of course you could. 1/8 times 10 to the negative 4. But I definitely want to get out my expression. The children jump up and down for joy when they see the expression. Or at least they should. Yes, I would do that. All right, so come up here. So the hydrogen. What's the matter? Well, why am I hearing sighs and disappointment here? Oh, I didn't write this out. My bad. All right, so they're gonna flippity. You did what?
I got the same thing.
I hope so.
I hope so.
All right, let's see. Let's zap all that. Whatever that is. Okay. 1.8 EE negative 4 times 0.4 divided by 0.6 gives me 1.2 times 10 to the negative 4.
Yep.
And it wanted the pH, so of course pH is negative log of the hydrogen concentration. So negative log 3.92.
Yes.
All right. Let's Starting off strong. I like it. So we'll box that in and color that so it makes all the children happy. All right. So there's A. Ooh, let's label it A. B says, okay. B says if 100 milliliters of this buffer solution is diluted to a volume of 1 liter, so they're adding 900 milliliters of water, the pH does not change. pH does not change. Discuss why the pH remains constant upon the dilution. What's that?
You can answer it because it affects everything. Because of water, you put a dash in the water. It has equal concentrations of hydrogen and hydroxide.
So when we add water, let's not use that color.
See, I remembered something from yesterday.
I'm proud of you. So it will change the concentration of these two things, correct? Changes it equally. So the ratio stays the same.
That's what I was trying to get at.
So if the ratios for these two molarities or concentrations change equally, it doesn't change anything that's going to affect the hydrogen concentration. Yeah, I like that. Very nice. So, what the? So distilled water changes both molarities, ratio remains the same. Voila. C. All right. A 5 milliliter sample of a 1 molar HCl is added to 100 milliliters of the original buffer solution. Calculate the hydrogen concentration of the resulting solution. Oh boy. Okay. So we know that our molarities are 0.4 and 0.6. Those are our molarities. So we have a couple things here. And I'll still use this. So we've got HCl, which is a strong acid, and that chlorine does nothing. So the hydrogen, we have 5 milliliters. 1 liter, 1,000 milliliters. 1 more? Is that what I read?
Yeah.
Okay. Thought it was. So that'll give me 0.005, or is there another 0? 0.05. Okay. Moles of H. The HCOOH. We have 100 milliliters of it. And that one was 0.4 moles per liter. And so that's 0.04? I do that right? I think so. Okay. What was that? I'm sorry. So we had 0.4 moles of the acid diluted in 1 liter of solution. So we're only taking 100 milliliters of the original.
Okay.
Yeah.
100 mil. Okay.
Yeah. So we're going to dip some out. But yeah. And then the COOH negative, 100 milliliters of that. And 1 liter, 1,000 milliliters. That one's 0.6. What's that?
Oh, it's in solution.
Okay. And then, so what is the total volume? Be careful.
105.
Yes. not 205. Okay. So 0.105 liters. Remember that the HCOOH and the COOH were already in that 1,000 milliliters or a liter. Poop. 105. So let's get some numbers here. So that is 0.0476, I think. Yeah. Yeah, we'll leave that in my calculator. 0.04 by 0.5. That is 0.381, we'll say. And then 0.06 is 0.571. All right, so those are our molarities. Oh, boy, I better write smaller. Now I'm going to do my ice chart over here. So let's get this. So HCOOH, H, and COOH. So the hydrogen, 0.0476. That's the acid, right? Away. Yeah. So 0.381 and 0.571. All right. So what do we do here? Good. So we're going to subtract by the hydrogen. Thank goodness it's smaller. So it goes to 0 and then reestablish its equilibrium. We'll find out what that concentration is here in a second. And then we'll add it to this side. So that, plus that, since I went the wrong way, 0.429. That minus 0.524. Yeah, I like that. Okay. Can we use Henderson Hasselbalch? Yeah, you could if you wanted to. Or we could use this cat again. I'm going to use Henderson. What the heck? So let's go. So pH equal to pKa of the log, the anion, or the HA. So pH is equal to negative log of 1.8 times 10 to the negative 4 plus log of, who is who here? So 0.52 is my anion. Okay. 2.4. And the other one's 4.29. Now, when doing it on your calculator, this is order of operations pretty good. So we'll find the pH first, which is kind of fun. So negative log 1.8 E negative 4 plus log. Oh, nope, don't type that in. That divided by that. So I get 3.83.
Yes.
Okay. And then to find, 3.83. What the? And then to find the concentration, I believe it's asking for. Take the anti-log negative 3.83. I like it. 1 point.
Like, if I would think Ka equals whatever, and then instead of equal to the Ka value, and then found the hydrogen concentration.
Wait, what? Say it again. Say what you just said.
Okay, I did Ka
Uh-huh.
equals the hydrogen concentration times 4 divided by 0.429.
If you did the,
Did you do the log of it though?
yeah,
I wasn't doing.
you put the
Wait,
the one that's the acid, but it.
Did you flip-flop?
The acid and the.
Did you use this Ka?
no, that's not flip flop, because then it would go.
No, she
Yes.
did. She said that she multiplied the anion by the Ka value
Well-
first, and then divided by the one on the bottom. Or divide by the one, or you multiply by the one on the bottom, then
Well,
divide by the one.
Okay, when I got hydrogen. then I put that in.
So for you, it would have been this. Hang on here. Let's.
I got the same thing when I mean, I used Tinder's list and I checked it.
So what was it again? The 524. So
54 COH.
yeah, so that's 524. So that would be on the bottom. Is that what you did?
Yeah.
Okay. And then the 0.429. So when I type that in, 1.8 E negative 4.
Because I didn't do that. Hang on.
Didn't do what?
Something.
Divided by.
Oh, yeah.
Okay, I got it.
I did too.
I think my way was faster, right?
Your way was, I don't know. Was it?
Because then the hydrogen concentration, you automatically get the hydrogen concentration.
I mean, tomato.
But I wanted
I
to
mean,
make
this
sure.
one you only have to like plug values into an equation. and that's
Right.
what you can't type on. Like,
Here you didn't have to write that.
Well, okay, anyway, I was just seeing, because then once I got the hydrogen, I felt like I had to find pH. And I-
Oh, no,
Right,
yeah.
exactly.
Okay.
And so then, but then when I did the anti-lock, I didn't,
She didn't pull it down.
I know, I didn't.
Ah, I got you.
And so
Okay,
then I got a slightly different answer. I was like, why do I have different hydrogen concentrations?
gotcha.
I figured.
Okay. And then
this is my flaws.
part D, that's where we're at, D, right? Okay. So it says 800 milliliter sample of a 2 molar formic acid, that's beefy, is mixed with 200 milliliters of a 4.8 molar NaOH. Calculate the H3O plus from the resulting solution. Yaza. I know. So let's find a couple things here. So number one, we're going to have this as our equation. I hope everybody sees. So HCOOH plus OH, right? Because we always want to make sure the hydrogen, the strong acid or strong base is always on the right side of the equation. Okay, so let's see. What did we have? 800 of a 2 molar. So 800 of a 2 molar. I'll do that down here. So 0.8 liters of a 2 molar. I believe that's 1 point.
The strong acid needs to be on the side or the right side.
The strong acid?
Did you-
Just the acid.
Oh, just the acid.
Yeah, the formic acid. In other words, an acid will always react with hydroxide. A base will always react with the hydrogen.
So why does it have to be on the right side? Is it just the-
Because when we write our KB, we want to make sure hydroxide is on top. Yeah. So that's that. So we got our first port, 1.6. What's that and that? And then, was it?
Craig, wouldn't that be moles on moles?
Oh, yeah, right. Yep. Thank you. Yeah, we still got some work to do.
be.
Okay. And then, so we have 2.2 liters of a 4.8, was it? More. So that'll give us, what is 0.96? Beefy. And then those are diluted in 1 liter. Okay. So now we've got 1.6 and 0.96, if I did that right. So the 1 liter came from the 0.8 and the 0.2. Add that up. Dash, we're going to say we have approximately 0 of that since we don't know what we're starting with there. Do we have a strong in this? Strong base, yeah. So now we're going to subtract by the smaller of the two, which happens to be the base. Thank goodness. 0.96 dash. Then we're going to add 0.96. So that one's easy. And that's a subtract. So 0.64. Can we use Henderson Hasselbalch?
Yeah.
You can if you want to. Now, I would.
Base one's different.
The what?
The base one's different.
The base one is different? What's that mean?
Hasselbalch, it's set up a little bit different.
Actually, no. I would use the same one.
Is it set up the same way as the acid? You just have that KD?
Well, let me ask you this. Do we have a concentration for the acid and the common ion?
Yes.
Do we know the original Ka value of the acid?
Oh, you can just use the KA as well. You can
That's
just
how
use the
sweet
KA.
this is. I know, right?
That's awesome. Okay.
So even though we have hydroxide in there and it wants to know, what is it ultimately asking for?
Hydrogen.
Oh, pfft,
Ah.
that's like a gift from the gods.
Yeah, it's not about-
But find the pH and then take the anti-log of it. Okay, so we've got, here, I'll just do it from here. Now, you're probably saying to yourself, could I write a KB expression? Yes. Could I find a KB value?
Yes.
Yes.
That takes too long.
It's okay. It doesn't take too long, but this is more exciting. So the negative log of 1.8. I mean, if you like adventure, this is where it's at. Now, who is my A minus that goes on top? 0.96.
The COO.
Yeah. And the HA is the H with the A. So the 0.64. So again, order of operation. So pH. Oh, baby. Um, 3.92 is what I got as well. So then the hydrogen or hydronium, whatever you want to do there, I don't care. Tomato, tomato is anti-log of negative 3.92.
Oh,
Negative 1 point. Oh, 1 point. Here, let's use a different color. 1 point. Dang it. Sorry. 1.19 repeating times 10 to the negative 4.
exactly 1.2.
Yeah, I got exactly what I got too, because I just used the value for my calculator.
Tisk, tisk.
Same thing.
All right, so that is 1982. How much time do we have?
Fine.
Oh, okay. Hang on, let me stop this. We have enough time.